B6, right? So this question asks the energy required to remove the outermost electron from sodium, Z equals 11 is 5.1 electron volts. Would you expect the energy required to remove the outermost electron from neon, Z equals 10, to be greater, less than, or equal to that of sodium? Explain using what you know about the electron configurations and the effective nuclear charge. Right, so if we look at the periodic table, right, sodium is right here. So the electronic configuration for sodium, right, is neon 3s1. Or if we were to like write it out, you know, so that we can directly compare the two of them, right, it's helium 2s2, 2p6, 3s1. And then in the case of neon, right, it's helium 2s2, 2p6 in that scenario. You know, the question's asking, right, would you expect the energy required to remove the outermost electron from neon to be greater? And that answer is yes, right? And the reason for that is that taking out that outermost electron is a real challenge because the Z effective is going to be higher on that neon electron compared to the one that the 3s is feeling. And the big approach to thinking about that is, you know, if you're looking at sodium, right? I'm just going to draw the, you know, very inaccurate Bohr model, but it kind of like, you know, shows what I'm talking about, right? You have your 1s shell right here, right, where you have your 2 electrons there, and then you have, you know, your 2 shell here, right? So you have your 8 electrons here in this case, 3, 4, 5, 6, 7, 8, right? And then you have your, you know, your 3 shell where your 3s1 electrons in, right? So you have this right here. In the case of neon, right, you only have the 2 shell and the 1 shell. So you have the 2 electrons here on the neon, and you have 1, 2, 3, 4, 5, 6, 7, 8 electrons around the neon, right? So taking off this electron right here, right, pulling that off is going to be easier because the amount of force, right, that this sodium is showing off, right? This sodium, you know, at its core, right, there's 11 protons right there, right? So there's 11 plus charge essentially, right? Whereas in the case of neon, right, there's a 10 plus charge. But in the case of this this electron right here, there's so many electrons that are shielding that, like all these electrons right here. Let me change the color. Right, all these electrons right here are all shielding this electron from that full 11 plus charge. And so the Z effective that electron is feeling is going to be pretty low, right? It's not going to be very large. Whereas in the case of the neon, right, there's only 2 electrons that are, you know, essentially fully shielding, you know, this electron from ejecting off, right, getting pulled off in that case. There's also all these other ones, right, that are kind of shielding at the same level, but they don't shield them very well, right? And so essentially the Z effective, right, the effective nuclear charge that you know, the outermost electron in neon is feeling is much, much greater than the Z effective that the outermost electron on sodium is feeling. And that's why pulling off, you know, an electron from sodium is going to be much more challenging compared to, well, not much more challenging, right? Pulling off an electron from neon is going to be much more energy intensive compared to taking off an electron from sodium from their outermost shell. But, right, once you get to that point right there where both of them now have the same number of electrons, taking off that second electron from sodium is actually going to be much higher in energy compared to neon because the Z effective that those new electrons, right, that these electrons right here feel is greater than the Z effective that the neon ones feel because, again, there's 1 extra proton on the sodium. So, you know, all of the subsequent ones where they're isoelectronic are always going to then be higher for the sodium, but that first ionization energy is going to be higher for the neon. In this case. So that's the reason why. And the way that, you know, you should think about and explain it. And it's the same thing, right, that happens too, right, if we go, you know, one step further down to argon, just going a little bit, you know, more advanced here, right, if we have argon here, right, so you're going to have 3 shells here. You have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Taking off an electron from argon, so argon is 18 plus, right, is still going to be less energy intensive than taking an electron off the neon. And the reason again for that is there's more shielding electrons in between that outermost electron and the nucleus. Even though the nucleus, right, has more protons, there's still more shielding electrons in between the two of them. And there's also the fact, right, that it's further away. And so if you think about like a magnet, right, the attraction between two magnets, right, the further away they are, right, the less it becomes. Right, that Coulombic attraction that you're going to be getting in those scenarios. So that's like another factor that goes into like why down a period, you also start seeing, right, ionization energies go downwards and stuff. So, but that's the reasoning, right? And the Z effective is also going to be affected as well. But that's